at the window of the space shuttle. One of the things we do at Williams College, which I'm proud to say is the #1 ranked liberal arts institution, college in the United States, is we work with our students doing research projects. And we had 6 undergraduate students with us, and then I have some professional colleagues. And we worked with Professor John Siridakis from Thessaloniki, and we had a number of other scientists collaborating. And we hope to organize a scientific group for the Chinese eclipses. Here is a main group of my students and the immediate colleagues on the deck where we were standing at the edge of the port of Castellorizo. The harbor comes in here, and in the background you see Turkey. Here is some of the larger group of students and workers. It is thinking. So we had with us 3 major experiments. One to study oscillations in the corona, to look for very rapid oscillations. We used these 2 telescopes, a computer, it was in the previous slide here, the 2 telescopes here, to look at 2 different emission lines that come from the solar corona. Here's my colleague Bryce Babcock there. And then we had a Fabry-Perot filter that gave very high precision, a very narrow wavelength images of the solar spectrum. And we can use that to find velocities in the corona. And here's Megan Brooke is a senior thesis student with me now working on these data. Here Shelby Kimmel is one of the students, is looking at the computer output from the oscillations. Here is the port and harbor of Castellorizo, and here I am silhouetted against the sky. The eclipses are so dramatic, it's always hard to remember how small they actually are in the sky. But the phenomenon where it goes dark in the middle of the day with 100% eclipse is quite different from the 16% eclipse that you had here today. You don't really even notice the eclipse till the sun is about 90% covered. The clouds make a big variation in brightness, and the human eye adapts to that. It's only when you get down to the last couple of percent that you really notice that something is going on. In the meantime, you need solar filters to protect your eyes, or use methods of eyepiece projection. But when the sun is entirely covered, when the solar photosphere is entirely covered, the last valleys on the edge of the moon allow some beads of sunlight come through. The last bead is so bright against the dark sky that it's known as the diamond ring. This is the diamond ring effect. The band is made by the inner part of the corona. The corona is both a difficult and an easy object to photograph. It's difficult because it changes in brightness by a factor of over 100 from here to here. And so it's very difficult and impossible to get it all on a single piece of film without some special techniques. It's easy to photograph because whatever exposure you use is good. A short exposure gives you the inner part, a long exposure gives you the outer part. You may overexpose the inner part, and there are some techniques we use to overcome that, but here is just a longer exposure. And you begin to see structure in the corona, which is actually the sun's magnetic field, holding the hot coronal gas in place. One of the things we do in eclipses is to try to get some images back right away to popular sites, and to work with NASA to link our eclipse observations with their space observations. We did have one of our compound images put right on the Sky and Telescope website the day of the eclipse. And you can improve the contrast and improve some of the structure that you see by processing in various ways. So here is adding 19 of the best images, and you'll see some future processing, some later processing there. We did merge our image with the space images from the NASA and the European Space Agencies Solar and Heliospheric Observatory spacecraft. And SOHO has one set of instruments that takes images of the sun through different filters that can show you the face of the sun. And it has a coronagraph that can hide the sun, but it has to hide more than the exact photosphere, a visible surface of the sun, because the inner corona is so bright it just scatters all around, it prevents you from seeing the outer corona. And so what we can do in the days of eclipses is provide, as we have here, the link between the SOHO inner and outer instruments, and we can then begin to follow the whole range of streamers in the corona from where they're formed on the sun to all the way out as they come into interplanetary space. Of course, half of them have an origin on the backside of the sun, so you can see the roots of half of them on the surface of the sun. I hope many of you know about Astronomy Picture of the Day, and we're glad to have our image used there. If you don't know about it, just search for Astronomy Picture of the Day with Google, and it comes right up, and you'll be able to look every day. And 2 days after the eclipse, this same compound image here was Astronomy Picture of the Day, and you can really see the streamers continuing from where they're formed. And it's interesting to study the region where they're formed and where the solar wind is formed, and to follow those to the outer part of the corona. Now, my colleague Jonathan Kern has perfected a method that was pioneered by others to have a special filter that is very dense here and is completely transparent here. And by trial and error and equations and over a period of years, he has the right overall formula to match the average fading of the corona. And so on a single piece of film, he can get this image, which shows so well the polar tufts and shows well the streamers over a very wide range, even though it's over 100 times brighter here than it is over here. And to do that, his filter that he makes himself varies by a factor. This is from 1 to 100 over this range here, which only goes out about 3/4 of a solar radius above the edge of the sun. So it's a very good trick, and you have to have things perfectly aligned during the eclipse for that to happen. But when you do, it really comes out magnificently. And here he's worked with Wendy Carlos to put together several of his images and color correct it. You can really see the structure of the corona very, very well. You can see the polar tufts, you can see the streamers extending far out into space. It's just a beautiful image. Next to his telescope, he had a camera that just showed the condition of the sky, and we didn't have completely clear sky on Castellarazo for 3 minutes of totality. The first 2 minutes are pretty clear, but then the last minute it got more cloudy, and we didn't really see the end of the eclipse. But fortunately, we had more than enough data to study, so we lost the very end there over the mountains. We were working with various Greek astronomers and students and amateur astronomers, and here's one of them took this beautiful diamond ring photograph, which was also Astronomy Picture of the Day. With us, one of my colleagues took some pictures that showed very well not only the polar tufts, but also some prominences on the edge of the sun. These are intermediate in temperature between the photosphere and well, not all the way to the corona, but they're a little hotter than the photosphere, and because they're sticking off the edge of the sun, we can see them in emission, and we see mainly the red line of H alpha with H beta and some other lines mixed in, so they look pinkish on the edge of the sun. These are examples of phenomena that vary with the sunspot cycle. I told you about our series of images in one of the spectral emission lines, and this is a movie we've made over the 3 minutes. And the movie has a line, and what we want to follow is changes in brightness and look for periods and change the brightness of some of these features. So we have this in the so-called red line, which is at 6374 angstroms, and the famous coronal green line at 5303 angstroms, which was discovered at an eclipse in the 1860s, or 1870s. Okay. So we have a lot of work to do in getting Fourier transforms of those images to try to find periods. We have some indications from past eclipses that there are some periods as short as 1 second or so, and we started on this because some of the theories indicate that we should have short periods like that, and others don't expect short periods like that. So again, we're looking for discrimination among theories of coronal heating. There's a wonderful spacecraft called the Transition Region and Coronal Explorer, acronym TRACE, that gives high resolution of observations at the edge of the sun. And fortunately, this active region came around that we observed also. So we have highest resolution from TRACE. Spatial resolution, we have highest spectral resolution from our Fabry-Perot experiment. We have highest time resolution from the movie that you just saw, which shows this same region. So we do what we can during the eclipse. The few days before, this is 4 days before the eclipse, this last active region rotated around the edge of the sun, and the sun was really very, very quiet. We just didn't know where we should look. Should we look here? And then just 2 days before the eclipse, this little active region came around, so we changed our agreement with TRACE to look at this edge. And now this is eclipse day, and just on eclipse day, fortunately, an active region rotated around just on the edge, and that enabled us to get the photographs that you just saw, and for TRACE to get the photographs that you just saw. So we're working with the NASA spacecraft to do that. The day of the eclipse, you can see this first active region, and then the sunspots near the limb, and then those features sticking up over the limb. This is the view you just saw of the helium gas at around 60,000 degrees, and then SOHO also observes in the extreme ultraviolet at the gas at a temperature of 500,000 degrees, and 1,000,000 degrees, and 2,000,000 degrees or so. Here we see this active region on the limb. We see a coronal hole at this pole here, another little coronal hole near the middle, a region that's a little cooler and less dense in the corona. And by putting all these things together, we can tell about the temperature structure of the upper layer of the sun. This is the coronagraph image that I showed you before with our inserts. But this is, note the size of the sun, and this region that usually on a day-to-day basis is unfilled. And you can see today's image by going to the web, but there'll be a blank there. And in fact, they also on a stick have a piece that hides even a bigger area of the sun and shows you the features further out. And it's very nice to get a daily image, and you can see eruptions almost every day, but it still is helpful on the days of eclipses to fill in that gap. I mentioned that we were also interested in the spectrum. This is Fraunhofer's original diagram of the spectrum of the solar photosphere back from 1814, and it's crossed by, as he discovered, these absorption lines that we now call Fraunhofer lines. At an eclipse, on the other hand, this everyday surface of the sun is covered, and we see this corona, which is thin gas silhouetted against the sky. And Aris Vulgaris, one of the Greek colleagues and students there, took this spectrum, and so what you see then is the emission lines that come from the chromosphere here, and this is done without having the slit in the spectrograph because the bright stuff at the edge of the sun is narrow itself. So we call this a slitless spectrograph, and you can see the shape of the bright regions there, and then the coronal gas extends all around the sun, and so you get the complete image of the sun in the iron green line there in this slitless spectrograph. So there's a chromospheric line as opposed to the coronal line.